Hi everyone. At the heart of USS Missouri's might lies an advanced steam turbine propulsion system powered by robust Babcock and Wilcox boilers. These state-of-the-art boilers generated high-pressure steam that fed the massive steam turbines, converting thermal energy into mechanical power. This impressive setup enabled the battleship to reach speeds of up to 33 knots. But the power plant did more than just drive the ship. The turbines were also linked to generators that produced the essential electricity for every part of the battleship. This power was distributed throughout the vessel, ensuring that everything from navigation and communication systems to lighting and fire control operated flawlessly, even in the heat of battle. The ship's advanced steam turbines converted high-pressure steam into a staggering power output, around 212,000 shaft horsepower. Moreover, the turbine installations were a testament to the innovative spirit of the time. They balanced raw power with fuel efficiency, a critical consideration for long-range deployments. This balance allowed Missouri to cover vast distances while remaining combat-ready, demonstrating the sophisticated integration of propulsion and operational endurance. When the USS Missouri is moving forward, its propellers are configured to rotate in opposite directions to balance the torque generated by the powerful steam turbines. Typically, when viewed from the stern, the port side propellers rotate clockwise, while the starboard side propellers rotate counterclockwise. This counter-rotating setup helps to neutralize excessive rotational forces on the hull, enhancing the battleship's maneuverability and overall stability at high speeds. These propellers were crafted from high-strength materials designed to withstand extreme forces and minimize cavitation, the formation of vapor bubbles that can reduce efficiency and cause damage. Their carefully optimized shape allowed Missouri to smoothly transition from slow maneuvering to high-speed operations. Additionally, the layout of the propeller shafts provided a level of redundancy. Even if one propeller encountered issues, the others could continue to drive the ship effectively. On USS Missouri, the propulsion system was a marvel of World War II naval engineering. The Babcock and Wilcox 8 boilers were strategically arranged within the engineering spaces to produce the high-pressure steam required to power Missouri's steam turbines. Adjacent to each boiler was its own dedicated fire room, a vital control center where engineers carefully monitored and managed the combustion process. In the fire room, they regulated fuel and combustion conditions to ensure optimal steam production, a task that was essential not only for efficiency but also for safety. The 8 boilers were positioned in separate compartments throughout the ship. This spread-out arrangement meant that if one compartment were compromised by enemy fire, the remaining boilers could continue generating the high-pressure steam. The high-pressure steam from the boilers was fed into 4 steam turbines, each connected to a separate propulsion unit. These units were linked to 4 propeller shafts equipped with counter-rotating propellers. Similarly, the 4 steam turbines were also distributed across different engine rooms. This not only balanced the overall weight and stress on the ship's structure but also provided redundancy. At normal cruising speed, steam was transmitted to the 4 engine rooms using 4 boilers. For higher speeds, all 8 boilers were lit. To further safeguard these critical areas, the battleship was designed with extensive compartmentalization. The engine spaces were divided by robust watertight bulkheads, each fitted with self-closing doors. These features were designed to seal off compartments in the event of flooding. Thanks to the redundant layout, the engineering team was able to shift the load and reroute power from the unaffected boilers and turbines, ensuring the ship maintained its operational capabilities even under duress. Since we've already discussed crew safety, it's worth noting that the ship's design has incorporated numerous emergency trunks throughout the vessel for crisis situations. Located in the lower sections of the ship, these were self-contained, watertight compartments. Equipped with robust, self-closing doors, they helped prevent water ingress by isolating any flooded areas. Their design ensured that personnel could quickly move from the lower decks to a safe zone or even directly into the sea. These emergency escape trunks were an integral part of a broader system of compartmentalization, enhancing the overall safety and survivability of the vessel. Welcome to the main armament section of our deep dive into the USS Missouri. Okay, so the USS Missouri had 9 16-inch Mark 7 guns, arranged in 3 turrets. The turrets were designated A, B, and Y, with A and B positioned forward and Y at the aft. The guns could target enemies at distances over 20 miles, piercing up to 18 inches of armor, effectively crippling even the most robust enemy warships and fortifications. Each Mark 7 gun operates on a sophisticated breech-loading mechanism that begins long before the shell reaches the barrel. Ammunition, massive shells and carefully measured powder charges were stored in secure, climate-controlled magazines deep within the ship. From there, an intricate system of chutes and hoists transported the shells and powder to the turret's ready room. When a firing order was given, the gun loading crew would transfer the shell and the precise powder charges into the gun's breech. During this process, strict protocols ensured that every component was correctly aligned and secured. The turret's advanced sighting and fire control systems, such as the Mk-38, played a crucial role by continuously monitoring target data and confirming that the gun was accurately aimed and ready to fire. Once the turret commander received confirmation that the gun was both loaded and properly aligned, he would activate the firing mechanism, often through an integrated electrical or hydraulic trigger system. This final command sealed the breech, and the powder charge was ignited. The resulting explosion generated immense pressure that propelled the shell out of the barrel at extraordinary speeds. After firing, an advanced recoil system absorbs the shock and quickly returns the barrel to its original position, readying the gun for the next shot. Reloading the Mark 7 guns was performed only when another shot was required. The process was highly coordinated with the ship's advanced fire control system. Here's how it worked. Once a target was acquired and the fire control system calculated the firing solution, the turret commander would determine the number of rounds needed in a salvo to effectively neutralize the threat. This decision was based on factors such as the target's range, type, and armor thickness, as well as tactical directives received from higher command. The turret commander typically relied on real-time data provided by the fire control director, which continuously updated targeting information. This allowed him to set a predetermined salvo count, often a series of 3 or more rounds, ensuring that each shot contributed to the overall battle plan. As soon as a round was fired, the gun crew began the reloading process immediately. The crew ejects the spent shell casing and carefully loads a new shell with its corresponding powder charges into the breech. Under optimal conditions, this process allows the gun to fire approximately 2 to 3 rounds per minute, a remarkable feat considering the size of the ammunition and the complexity of the loading sequence. In summary, the turret commander knew how many shots to execute based on calculated fire control solutions and tactical orders, and reloading was efficiently performed only when the next shot was needed, maintaining a rapid and effective rate of fire during combat. The 16-inch Mark 7 guns of the USS Missouri were capable of firing a variety of shells, each designed for a specific role in naval warfare. These projectiles, weighing over a ton each, were carefully engineered to maximize damage, range, and effectiveness against different types of targets. The most powerful shell in the battleship's arsenal was the Mark 8 armor-piercing shell, weighing 2,700 pounds. This shell was designed to penetrate the thick armor of enemy battleships, cruisers, and fortified coastal defenses. The Mark 8 AP shell had a hardened steel nose cap and a delayed action fuse, allowing it to pierce over 30 feet of reinforced concrete or up to 20 inches of battleship armor before detonating inside the target. With a muzzle velocity of 2,500 feet per second, it could strike enemy ships at distances of over 20 miles with devastating effect. During World War II, these shells proved their worth in battles such as the Battle of Leyte Gulf. For softer targets such as unarmored ships, shore installations, and troop concentrations, the battleship used the Mark 13 high-explosive shell. Weighing 1,900 pounds, the Mark 13 carried a much larger explosive charge than the armor-piercing shell, creating massive blast effects upon impact. During the Korean War, Missouri sea shells were instrumental in supporting ground troops by destroying enemy bunkers and artillery positions along the coast. In night combat, visibility was critical. The USS Missouri could fire star shells, which were essentially illumination rounds designed to light up the battlefield. These shells contained a magnesium flare, which ignited in midair and illuminated a wide area for several minutes, helping gunners locate enemy ships and shore targets in darkness. Star shells were often used in combination with radar-assisted fire control systems, ensuring that Missouri's guns could operate effectively even at night. During the Cold War, battleships were briefly considered as platforms for tactical nuclear artillery. The Mark 23 KT nuclear shell was developed for 16-inch guns, capable of delivering a low-yield nuclear explosion at long range. While never deployed on USS Missouri, the concept demonstrated the versatility of these massive naval guns, even in the nuclear age. The USS Missouri's Mark 7 guns were among the most formidable naval weapons ever built. With a variety of armor-piercing, high-explosive, illumination, and even nuclear shells, they could engage any target, from heavily armored battleships to distant shore fortifications and moving enemy fleets. The Mk-38 fire control system was the technological brain behind the 16-inch Mark 7 guns on the USS Missouri. Designed to deliver pinpoint accuracy at extreme ranges, this system was a marvel of World War II-era engineering, integrating advanced optics, radar tracking, and mechanical computing to ensure devastating firepower. At the heart of the system were two Mk-38 gun directors, positioned high on the ship's superstructure to provide an optimal line of sight. Each director was equipped with a Mk-48 rangefinder, allowing operators to visually track targets over long distances. As radar technology advanced, the Mk-13 fire control radar was added, significantly improving target acquisition, especially in poor visibility conditions or during night operations. Once a target was identified, the system measured its range, bearing, and speed. These calculations were then relayed to the ship's Mk-8 fire control computer, located deep within the armored plotting room. This electromechanical analog computer was responsible for processing vast amounts of data in real time. It factored in variables like the ship's own speed and course, the target's movement, the rotation of the Earth, wind speed and atmospheric conditions, and even the wear and tear on each individual gun barrel. Using these inputs, the computer continuously refined firing solutions. Once the fire control computer calculated the firing solution, the data was automatically transmitted to the turret control stations. Inside each turret, operators adjusted gun elevation to achieve the correct trajectory, turret training to align with the moving target, time fuses when using high-capacity shells for air bursts. At the command of the ship's gunnery officer, the massive 16-inch guns fired, launching shells that could weigh up to 2,700 pounds at speeds exceeding 2,500 feet per second. Unlike earlier battleships that relied purely on optical range finding, Missouri's radar-directed fire control enabled her to engage targets beyond the visual horizon. Radar operators monitored shell splashes and relayed corrections in real time, allowing for quick adjustments and successive, more accurate volleys. Missouri's fire control capabilities remained cutting-edge well into the Cold War, proving the effectiveness and durability of the Mk-38 system across decades of naval warfare. In this video, we explored its propulsion system, the operation and reloading of the powerful 406mm Mark 7 guns, and the advanced Mk-38 fire control system that ensured precise main battery fire. Thank you for watching and joining us on this deep dive into naval engineering. In the next part of this series, we will continue our exploration by covering secondary armament and anti-aircraft defenses, as well as the combat information systems and ship command structure that ensured Missouri's effectiveness in battle. Make sure to subscribe and stay tuned for the next episode.